Other differential equations for real-world applications, Newton's law of cooling problems. Our objectives for this lesson are write a differential equation to model Newton's law of cooling. So what is Newton's law of cooling? So we'll begin with that and we'll write a differential equation to model what the law states. And then once we have the model, we'd like to solve the differential equation for Newton's law of cooling. That would give us what we call the general solution of the differential equation, and then find the particular solution that fits given data in a particular problem. So let's begin by looking at what the law states. So here's Newton's law of cooling, and it states, Newton's law of cooling states that the rate of change meaning the derivative, whenever you see a rate of change, you're thinking the derivative of a particular function. The rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So look at these words that we want to pay attention to. So first of all, let's assign a variable. So we'll say let y represent the temperature of the object. Let y represent the temperature of the object. We can specify units for the temperature when we talk about a particular problem. And we'll let t represent time, and again we can specify units for t when we talk about a particular problem. For example, time could be measured in minutes or hours, etc. So the law states that the rate of change in the temperature, so the rate of change of y, because y represents the temperature, with respect to time, the rate of change in the temperature of an object, so I will write dy dt, because that tells me the rate of change of temperature with respect to time. How fast is the temperature changing for each unit of change in time? The rate of change in the temperature of an object is, so for the word is, I will have an equal sign, is proportional, so I will have a constant of proportionality, k. What is it proportional to? It's proportional to the difference, so I will have a subtraction. It's proportional to the difference between the object's temperature, which is represented by y. So I'll have it's proportional to the difference between the object's temperature, represented by y, and the temperature of the surrounding medium. So I'll just use maybe something like F. The temperature of the surrounding medium, and of course that would be a particular value in a particular problem. So that's what Newton's law of cooling states. The rate of change in the temperature of an object, dy dt, is proportional to the difference between the object's temperature and the temperature of the surrounding medium, and I'm using uppercase F to stand in for whatever the temperature of the surrounding medium is. So let's look at a particular problem. So here we have a particular problem. Let y represent the temperature, and now for this particular problem, the units for the temperature are degrees Fahrenheit of an object in a room whose temperature is kept at a constant 60 degrees Fahrenheit. So that's the temperature of the surrounding medium. I used F in my general differential equation for Newton's law of cooling. So F would be 60 in this problem. Now we have another sentence telling us that if the object cools from 100 degrees to 90 degrees in 10 minutes, how much longer, so after 10 minutes, we want to know how much longer after 10 minutes will it take for the object's temperature to decrease to 80 degrees. So how do we do this problem? Well, it's a Newton's law of cooling problem, so we'll begin with the differential equation given by Newton's law of cooling. So this is the differential equation given by Newton's law of cooling. the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium, which is represented by F. But of course, now I can replace F with 60 because that's the temperature of the surrounding medium that's given in this problem. And that's 60 degrees Fahrenheit. So what is it that we need to do in this problem? So we've done objective 1. We've already written a differential equation to model Newton's law of cooling. So what we need to do now is solve the differential equation for Newton's law of cooling. That will give us what we call the general solution. And then after we find the general solution, we need to find the particular solution that fits the given data. That would give us our particular solution, which you can also call our model for the situation. And then we're going to use our model to answer the question in the problem. So that's going to be our progression for the work that we'll be doing. So we can begin now to find the general solution of this differential equation. After we find the general solution, we'll use the information that's given here to find what we call the particular solution, or our model for this problem. And then after we have the particular solution, we can use our model to answer the question that's presented in the problem. So let's begin by solving this differential equation using the separation of variables technique, and this will of course give us the general solution. So we need to begin by separating variables. So I can multiply both sides of this equation by dt. That would give dy is equal to k times y minus 60 times dt. Now I see that I have y minus 60 here, so I want to get that together with dy. So I can multiply both sides of the equation by 1 over y minus 60. So when I multiply by 1 over y minus 60 on the right side, it will cancel with the y minus 60, leaving me with just k times dt. And when I multiply by 1 over y minus 60 on the left side of the equation, I will have 1 over y minus 60 dy. Now you can see that in this equation, the variables have been separated. So the y is with dy, and k is just a constant, and that's with dt. Having done that successfully, my next step would be to integrate both sides of the equation. And it's really easy to integrate the right side because you just have a constant. It's like having the indefinite integral of 5 dt. The antiderivative there would be just 5t plus a constant of integration. So on the right side, you're just going to have k times t plus a constant of integration. I'll write that in a little bit. On the left side, you're going to use the log rule for integration. So here is the log rule for integration, and you have y minus 60 in the denominator. If you wanted to, you could do a formal u substitution. But this is kind of easy to do mentally as well. So either you let u be equal to y minus 60, and du would be equal to dy. So it's kind of easy for that reason. But if you do that, or you do it mentally, you're going to get natural log of the absolute value of y minus 60 for your antiderivative. Of course, there is a constant of integration on the left side as well as the right side, but there's no need for us to have two separate constants of integration. We can just combine them and write one constant of integration on the right side. Before we go any further, let's consider the range of temperatures we have in this problem. So we begin with an object whose temperature is 100 degrees Fahrenheit. 10 minutes later, its temperature is 90 degrees Fahrenheit. And after how much longer will the temperature be 80 degrees Fahrenheit? So we're using this differential equation for a range of temperatures from 80 degrees to 100 degrees. And for that reason, y minus 60, because y is always greater than 60, y minus 60 will always be positive. And because y minus 60 will always be positive, I don't need the absolute value here. It's unnecessary for that reason. So I can write natural log of y minus 60 is equal to kt plus c sub 1. I would like to solve for y because y represents the temperature of the object, and that's what we're after. So how do we do that? We're going to exponentiate both sides of this equation with base e, because exponentiating with base e is the inverse operation of taking the natural log. So when we do that on the left side, the inverse operations will undo each other, leaving us with y minus 60, and on the right side we'll have e to the kt plus c sub 1. So y minus 60 is equal to e to the kt plus c sub 1. Using a property of exponents, you can write that as e to the kt times e to the c sub 1. What you have is a product of two powers with the same base, and when you have that, you can add the exponents, and of course that will give you what we had in the previous line. But the good thing about doing this is that you see that you have e to the c sub 1, and c sub 1 is just a constant, an arbitrary constant. So e is also a constant, so e to the c sub 1 is just a constant. And we're going to simplify our model by just having c, because this is just a constant. So we now have y minus 60 is equal to e to the c sub 1 is just a constant times e to the kt. And of course, we want to get y by itself. That's representing the temperature of our object. And all we have to do now is add 60 to both sides of the equation to isolate y. And what is this? This is our general solution. This is our general solution of the differential equation, which is Newton's law of cooling. And in fact, except for the 60 here, all of the general solutions for Newton's law of cooling problems will have this form. But of course, you'll have whatever the temperature of the surrounding medium is instead of 60, which is the case for this particular problem. You may remember that I initially wrote my differential equation for Newton's law of cooling with F standing in for the temperature of the surrounding medium. So whatever that is what you'll have here. So now we have our general solution of the differential equation for Newton's law of cooling for this particular problem. So what do we have to do next? The next thing that we have to do is to find the particular solution that will fit the given information in this problem, and then finally to use that particular solution, which is the model for the problem, to answer the question. So what is the given data in this problem that will help us to find the particular solution? So what we have here are ordered pairs of the form T for time and Y for temperature. And we know that time is going to be measured in minutes. How do we know that? How do we know that time is measured in minutes? T is measured in minutes. The way we know that is because of the information that's given in the problem. You can see that temperature is given in degrees Fahrenheit right here, and you can see that time is measured in minutes. So we have ordered pairs for time and temperature. So let's read the information that we have here. It says here, if the object cools from 100 degrees Fahrenheit to 90 degrees Fahrenheit in 10 minutes. So initially, the temperature of the object is 100 degrees Fahrenheit. So initially, time is 0. At the time that our observation begins, time is 0 minutes, and the temperature of the object is 100 degrees Fahrenheit. And 10 minutes later, the temperature would be 10, and the temperature of the object will be 90 degrees Fahrenheit. So that's our given data. So we need to find the values of C and K that would fit this given data. And doing that is called finding the particular solution of the differential equation. What we have now is the general solution, and we will now find the particular solution, which will be our model for this problem. And then we can use that model to answer the question, how much longer will it take for its temperature to decrease to 80 degrees? So you will begin by substituting 0 for t and 100 for y in the general solution. So substitute 100 for y and 0 for t. So I have c times e to the k times t, k times 0 plus 60. Now, k times 0 is 0, so you have e to the 0, which is 1. So that gives me 100 is equal to c times 1, or c plus 60. And when you solve for c, you subtract 60 from both sides of the equation. 100 minus 60 is 40. So you get c is equal to 40. Now we have to solve for k. So you'll see that I write this equation using the value that we just found for c. And now we have to solve for k. So what have we not used yet? We haven't used this piece of information. So now we're going to use that to help us find k. So I need to substitute 10 for time, 10 minutes for time, and 90 degrees Fahrenheit for temperature. So y represents temperature, so I write 90 is equal to 40 times e to the kt, k times 10, or 10k, plus 60. And I will solve this equation for k, and that will tell me what k should be. So how do we solve this equation for k? We want to get k by itself, so you have to undo the operations that are being done on k. So let's identify what's being done on k. So we have our order of operations, grouping symbols, exponents, multiplication, division, addition, and subtraction. So you can see that you have exponentiation with base e. You also have multiplication by 40, and you also have addition by 60. So you have these three operations that are being done. So you have to undo them in the reverse order of gamdas. So you have to begin by undoing addition by subtracting, undoing multiplication by dividing, and finally we will undo the exponentiation with base e. So we will begin by undoing the addition of 60 by subtracting 60 from both sides of the equation. 90 minus 60 is 30, and when you subtract by 60 on the right side of the equation, 60 minus 60 is 0. The next thing that we need to undo is the multiplication by 40. We will undo that by dividing both sides of the equation by 40. So that will undo multiplication by 40, leaving us with just e to the 10k on the right side. And on the left side, we have 3/4. 3/4, you can write that as 0.75 if you'd like. 3/4. 30 over 40 reduces to 3/4, which is 0.75. Now we will undo the exponentiation with base e. How do you do that? You have to take the natural log. That's the inverse operation of exponentiation with base e. And when you do that, this is what you have. So on the right side, you will just have 10k because natural log and exponentiation with base e are inverse operations. And on the left side, you have natural log of 0.75. And finally, you can solve for k now by dividing both sides of the equation by 10. So you get k is equal to the natural log of 0.75 over 10, which is approximately equal to negative 0.02877. And if you want to keep more digits after the last 7, that's a good idea. But you definitely don't want to round any more than what you see here, because that will introduce rounding error. So now we actually know the value of k, so we have the particular solution of the differential equation for our problem, which is our model for the problem. So how do we conclude this problem? Well, we have our model for the problem. We have our particular solution that fits the given data in this problem. So now we need to use that to answer this question. How much longer will it take for the temperature of the object to decrease to 80 degrees? How much longer? So currently the time is 10 minutes. So when we solve our equation, we'll get a value for t, and then we'll have to subtract 10 from that because the current time is 10 minutes. The t from the answer is since 0 minutes. So how much longer from 10 minutes will it take for the temperature to decrease to 80 degrees? So when will the temperature be 80 degrees? That's basically what we want to know. And how much longer is that after the first 10 minutes? So we set y, which is the temperature, equal to 80, and we solve this equation for t. That's what we need to do. So let's take a look at how that is done. And then when we have t, that'll tell us the time at which the temperature will be 80 degrees. But the question is asking how much longer from t is equal to 10 minutes will the temperature decrease to. How much longer will it take for the temperature to decrease to 80 degrees? So we get the time, and from that we need to subtract 10 to answer the question. Okay, so let's go ahead and begin by solving this equation. It's similar to what you saw earlier when we were solving for k. You have to undo the operations that are being done on t. So let's identify what's being done. Well, you have exponentiation with base e, you have multiplication by 40, and you have addition by 60. So to undo these operations, you have to undo them in the reverse order of gamdas. So you have to begin by subtracting 60 from both sides of the equation, dividing both sides of the equation by 40, and then you have to undo the exponentiation. So subtract 60 from both sides of the equation. 80 minus 60 is 20. And that would give us what we have here now. Because 60 minus 60 on the right side would be 0. And then we need to divide both sides of the equation by 40. 20 divided by 40 is 1/2. So we have 0.05. And on the right side, 40 and 40 will cancel, leaving us with e to the negative 0.02877t. And finally, we have to undo the exponentiation with base e. So how do we do that? We take the natural log of both sides of the equation. And when we do that on the right side of the equation, that would give us negative 0.02877t, and on the left side of the equation we have natural log of 0.5. So finally we need to solve for t. Divide both sides of the equation here by negative 0.02877. That gives us t. So t is approximately equal to natural log of 0.05 divided by negative 0.02877. And you want to use your calculator and get a decimal approximation for that. So that's about 24.09 minutes. So let's go back to the problem to see how we should answer it. So we just solved this equation and we found that t is approximately 24.09 minutes. That means about 24 minutes from the beginning, the temperature of the object will be 80 degrees Fahrenheit. But the question is asking how much longer from 10 minutes will it take for the temperature to decrease to 80 degrees? Well, subtract 10 from 24 and you get 14. So it's about 14 minutes, 14.09 minutes later from this time, the temperature will decrease to 80 degrees Fahrenheit. So that would be the final answer to our problem here. So you're going to write about 14.09 minutes. So in this problem, we began by looking at Newton's law of cooling. We wrote a differential equation for it. We solved it to find the general solution of the differential equation. And then in this particular problem, we used the given data to find the particular solution that satisfied the given data, which became our model for the problem. And we used our model to answer the question that was posed in this problem.